So this tutorial I've titled it Putting Weekly Crop ET Reports to Work for You. About a little over 2 weeks ago on April 3rd, we had our first tutorial, and these were the subject matter that we covered. Basic ET concepts, then how to read the ET report tables that we send out by email and make available online through our SacramentoValleyOrchards.com website. We also talked about, as well as getting familiar with the table, what the numbers mean, navigating through them. Talked about how to pick an irrigation efficiency factor, because that weighs in reading the table. And then we went through a number of conversions, how to convert ET estimates from inch per acre to gallons per tree or vine. And then we ended up with teaching how to do some calculations to relate the weekly ET rates that we report to you to your specific irrigation system design to determine an irrigation runtime. If you were unable to participate in that tutorial and would like to see the video, the web link is here, as well as the PowerPoint link. And when this tutorial is over, we will be following up by sending out a copy of this PowerPoint as well, and the video. So moving on, picking up from tutorial 1, again, the emphasis is on the soil perspective. I want to talk in this hour why consider the soils perspective. I'm going to introduce you the idea of a concept of a water budget or water budgeting and how our ET reports are part of it. We're going to show how to use a water budget to track soil moisture depletion in your orchard. And then we're going to talk a little bit, give some examples on how to pair these water budgets that we're going to learn to do with actual soil moisture monitoring in your fields. And then we'll wrap up with a common question that's kind of tied to the soils, and that's how to adjust for different irrigation wetting patterns with different irrigation systems, whether it be drip, micro sprinkler, or a solid set sprinkler. So as we consider the question of why the soils perspective, the first thing I think we all recognize that soils store water from the rainy seasons from November through April, thereabouts, and it's available to be used during the growing season later in May, June, July, and even later if we can preserve it. It may or it may not be a substantial part of the seasonal crop water demand, and can potentially impact your power bill and water savings. It depends on the crop root zone of your specific orchard, the soil characteristics, and the weather for the year in question, the amount of rainfall that we receive. The soils are also important from the standpoint that they control how water infiltrates and percolates through the root zone, which in turn affects soil aeration as the roots are growing and affects the tree and crop root health. So if we were to just blindly budget our irrigations by matching ET 100% based on our irrigation system design, we would increase our chances quite a bit of over irrigating by not considering the soil storage capacity, the root zone capacity of our crop. So then kind of moving forward, I want to introduce the concept of what is water budgeting. It's something I think it's pretty generally easy for us to grasp because we do it day to day with our own monetary budgets, our own finances. It's an accounting process where we account for the crop water demand with our ET reports, and we compare it against and balance it against all the water supplied to the crop, that being our irrigation water, as well as our rainfall, and sometimes other sources of water like seepage if you happen to be in the proximity of a river, creek, or have some kind of shallow water table effect. Our weekly ET reports that we send out to you inform the water demand side of the water budget. And with a water budget, I kind of already alluded to this, but we're looking to balance, to seek a balance, not a surplus or an overdraft. And I hope by the time this tutorial is done, I'll have demonstrated what we mean by that. A water budget is also a method of estimating or tracking the soil moisture depletion, and that's what we're going to concentrate on for most of this tutorial. The goal is to not oversupply the soil with water, making it too wet and saturated, nor undersupply it and causing it to be too dry for too much of the season. And again, we're trying to strike that balance for optimum soil moisture condition for the best chance of a sustainable crop from one year to the next. So the question of why use a water budget to estimate soil moisture depletion? For one thing, if you're just kind of getting introduced to using science-based techniques to irrigation management, this is among the simpler techniques and a good place to begin trying to figure out how to integrate science into your irrigation management decisions. With our ET reports and with your knowledge of your irrigation system, and as you'll learn today about evaluating your soils, it's a relatively inexpensive on-farm management approach. The information is for the most part free to you. What's the cost is your time and investment of learn how to put it all together and use it. A water budget is a way to estimate and anticipate soil moisture conditions and irrigation needs. So it is a mechanism to kind of plan ahead. A budget does lend itself to tracking and reporting irrigation management practices, and the reality is that we in agriculture are being asked more and more to report our practices for various regulatory reasons. And one of the things about a water budget, it's being looked at or taken as from a ranch or field big picture point of view of your irrigation management. And a little bit later, I'll contrast that to soil moisture sensors. So let me see if I can move this just a little. So many of us may be familiar with our NRCS soil survey maps. This is a map of some farmland on the west side of Tehama County. Those yellow lines, the squiggly lines, they represent contour lines that represent kind of just the natural random patterns of the soil variability of these farmlands. And the initials that you see within those yellow contour lines, like the MF is Maywood, AW is Arbuckle series. These represent different soil types, different soil structures, different water holding capacities. I just included this map because I thought it was kind of interesting. It reminds us that the farmlands that we farm in our Central Valley, whether it's Sacramento Valley or San Joaquin Valley, are alluvial deposits, and they're older soils that have a long history. This is what's called a Veris soil variability map. Veris is a machine that can be towed through the orchard in transects about every third tree row or so, and or every 60 feet, and measure the electrical conductivity of the soil down to about 6 or 7 feet. And a soil that is higher in clay content, higher in water holding capacity, will give a measure of a higher electrical conductivity measurement than a sandier soil that has lower water holding capacity. And this technique allows us to map the soils, and here it's just you can really see how the alluvial processes affect our soil variability. The blue representing our lightest soils with a lot of gravel and sand, and the golden red rust colors are soils with a large fraction of silt and substantial clay content, and the greens and yellows being soils that are kind of in transition between those two extremes. So the idea behind the ET or the water budget is we're going to use a water budgeting technique to kind of come up with a soil water balance for the big picture across all this variability. A water budget gives us an estimate of the soil water balance from a completely different perspective than soil moisture sensors. On the left are examples of soil water tension sensors. This brand name is called a Watermark. It's one of the longer, one of the sensors has been around the longest amount of time. One of the more affordable sensors, just showing how this is the actual sensor here. This is how we kind of retrofitted them to put them in at different depths. In this case, 8 inches, 18 inches, 30 inches, and actually deeper. This is a kind of soil moisture sensor called a capacitance probe. Each one of these sensors, each one of these groups is a sensor that senses the soil moisture at these different increments, usually in 4 to 6 inch increments, down to at least 3 or 4 feet, maybe 5 feet. And so the point of putting this slide in this presentation is using a water budget approach is a big picture water balance technique for trying to track how you're doing with your irrigation. And here we're relying on sensors that only sense the soil moisture in a very small volume of soil. In the case of these tension sensors, only the soil that they touch is what we gauge the soil moisture by. In the case of these sensors, the technique might reach out at most 1 inch or so from the sensors. So, very sharp contrast between our water budget approach and our soil moisture monitoring as far as the scale of what we're actually monitoring. Okay, so along the way here to kind of keep us kind of all thinking and do time checks here a little bit, I've got 4 what we call knowledge checks, okay? So we're going to run a poll right now. The question that's being considered is, what is a water budget and how might one help with irrigation management? Okay, so the poll has been closed and here's how we've weighed in. So what is a water budget and how might one help with irrigation management? So about 1/4 of you have said it is an accounting of the crop water demand and all the water supply. And that's true. It's a method of estimating and tracking soil moisture depletion. It can be used in that fashion, and that's what we're going to show next. And it represents a ranch and field-wide picture of irrigation management, which is interesting. Most didn't feel, that no one felt that was the case by itself. And then the majority, 3/4, said it was fit all of the above, which in my mind, I think that's, I kind of see it as a tool that achieves all of the above. All right. So we'll keep going. So in order to perform a water budget and relate it to the soil conditions, we have to, as a first step, we have to assess the water holding capacity of your orchard soil. And this is a site-specific characteristic that goal is to help you to have the tools, know the skill set to assess this for yourself. Soils come in many kinds of, with many characteristics. To the left is one of our better soils. That is actually a Columbia loam soil profile, known to be a very deep profile, very uniform from surface to depths of 6, 7, 8 feet deep. The center picture is an Arbuckle soil series, a common ag soil on the west side of the Sacramento Valley. Tends to be recognized for having a fair amount of layering. It can have some sharp differences in texture between clay and soils with even the subsoils with a fair amount of gravel amongst the clay. And on the right is if I remember right, a Perkins soil series, which is a gravelly sandier soil up and down the profile, very hard and what we would call massive in terms of its just hardness and ease of tilling. So these kinds of characteristics we have to take into consideration. So what we're trying to evaluate by assessing the water holding capacity of the soil is its ability to hold water in the unsaturated phase. And so soils have, this picture would suggest two phases of water holding capacity. There's the saturated phase, which is occurring during heavy rainstorms or during significant irrigations. On the left, that's when the porosity of the soil is completely filled with water and there is no air in the soil. It's the condition that we do not want to prolong, particularly when the trees are growing and transpiring. It's one of the conditions that's within 48 hours, we can do some pretty serious damage and harm to the root health if the trees are leafed out and growing actively. At the saturated phase, that water will drain given 24, 48 hours. Gravity will remove that excess water and it'll move to the fill capacity state, which is the middle picture. At fill capacity, that is the optimum combination of high water content and aeration. The pore space is about 50% water and 50% air. On the right, the other extreme of the unsaturated phase of water movement is the point where none of the water is free to really move. It's called hygroscopic water, and it's being held so tightly by the adhering forces of the soil, the absorptive forces, that that water doesn't go anywhere and the plant has no chance at it. The only way we can remove it from the soil is to heat the soil with an oven in a laboratory situation on the order of about 250 degrees Fahrenheit. So when we relate this to the water holding capacity of an orchard soil, as I pointed out, we've got gravitational water. If you were to use that watermark sensor that I showed you earlier, it would be registering around 0 centibars tension. At around 10 to 30 centibars, 10 centibars if it's a sandy soil, 30 centibars if it's a loam or higher in clay content, we will be approaching what we call fill capacity. That's that 50% air, 50% water content. And then if we were to use that watermark sensor again, which has a range of 200 centibar, at that 200 centibar, we'd be experiencing a soil that's quite dry, approaching a level that we can no longer, because the adhesive forces of the soil, we can no longer extract water from it, and entering that hygroscopic or the water zone. It's this plant available water zone that is of interest to us and that we are trying to manage to get our crops to perform as best possible. When we're saturated, we have this gravitational water, the 100%, we're oxygen depleted, and this is a form of harmful crop stress. It can lead to death probably quicker, and the consequences more acute than the severe crop stress. It's a better chance of recovering from too much crop stress than from poor aeration. We get into the plant available water. What we're moving through, all through this phase, a plant can get water, but the drier it gets, the harder it has to work, and it's at the expense of energy, okay? We are trying to manage our water to keep our crop growing optimally in a low to mild stress condition. Sometimes there are benefits to even allowing moderate stress. We're learning benefits well documented in hull split, in almond. It's useful to allow some stress to help us control diseases and improve timing of some of our insecticide sprays. We're finding in walnut that we maybe get some benefit by allowing some mild stress in the early, in the delay of the first start of irrigation. And so there's different places some mild stress may be beneficial. There's a term called a management threshold or maximum allowable depletion. I'm going to refer to it as management threshold. For today's tutorial, I'm going to speak in terms of 50% management threshold. Essentially what we're doing is, so 50%, you can kind of view this as a gas tank, this being full, this being empty, and this being half full. For the most part, our crops will perform pretty well if it's growing in this range most of the time. I would say that this management threshold is a judgment call on your part. If you are concerned about losing deep moisture and running out of moisture, you may not want to go to a 50% management threshold. But if you're more concerned about over irrigating and oxygen depletion and effects of losing trees, you may be satisfied with a 50% management depletion. It depends a little bit on your management goals. So as I've already showed you, we have different soil physical conditions, texture, structures. With this comes different water holding capacities. So fine sandy loam soils will have less plant available water. Loam soils, your medium textures will have more water, and your silts and clay loam soils tend to have the most plant available water. And again, these dashed lines represent a 50% management threshold in this case. We offer just some generic tables to help you kind of pick that value. This is this citation here. You can find this online by Googling this title and the source. Here you can see that your sandy soils, fine sandy loams, have the lower plant available water, and your mid-range soils have higher plant available water. When you get to very high clay content, the plant available water actually declines just a little bit. You can also get, rather than using the generic tables, you can use seek out site-specific information. This is using Google Earth and the California Soil Resources soils information. This is the website that you can download the app from and link it with Google Earth, and you can identify your specific orchards. Here's a little example. Back to the farmland I showed you earlier. This is pointing to a contour that is a Tehama silt loam, and it starts to give us a link to more information about that soil. If I click on that link, it will take me to a page, and it will give me an estimate of the available water storage. In this case, 17.7 centimeters. Because this is in metric, I have done the math for you to make the conversion, showing you the 17.7 centimeters of water per, notice 100 centimeters, that's a meter, 3.3 feet. So I can first convert the centimeters of water to inches water. So 7 inches water. I second convert the 1 meter depth of soil to 3.3 feet soil. 7 inches of water divided by 3.3 gives you a water holding capacity of 2.1 inches of water per foot soil as an estimate. Here's another example. This is contours for the Arbuckle Gravelly Loam series in that same proximity of farmland. Here you can see it's 13.6 centimeters of plant available water in the top 3 1/3 feet, doing the same conversions. Here it's 5.3 inches of water total for that 3.3 feet. And working through the conversions, 5.4 inches of water divided by 3.3 feet is 1.6 inches of water per foot soil. So we do have these tools available for us that you can kind of go find your site-specific information and assess your own water holding capacity for your own orchard. So after assessing the water holding capacity of the soil, there is the question of what is the effective root zone of a perennial tree crop. And there are a lot of observations and opinions about this. Much less quantitative data. We now have scientists that are using cameras and counting the roots and learning that they actually come and go in flushes and regrow, learning a lot more, and hopefully in times ahead we'll be able to get more quantitative about how to assess and judge our root zones for our tree crops. I would say this, it is certainly deeper than can be evaluated by quickly digging in with a shovel and looking at the moisture that's oftentimes supporting the resident vegetation in the orchard. I suggest using at least 4 feet as an effective root zone for 3-year-old trees and older. A little bit later, I'll show you a snippet of data as to why I suggest this. The UCANR publication 8571 suggests as much as 8 feet. And then we've worked in some experiments on farms in the Sacramento Valley that we've seen evidence that the root systems can be as deep as 10 feet or more. So it's judging the effective root zone is really a tough call. You do the best you can, and you remember that if things don't quite add up after a year of running a water budget, that this may be one of the most pivotal points to reconsider. So here's an example of how to estimate the plant available water for an orchard. Question is, what is the plant available water holding capacity for orchard A1 with a 50% management threshold? The orchard is growing on a Tehama siltloam series with available water storage capacity of 2.1 inches per foot soil. The effective root zone is 7 feet. So for this orchard, 7-foot root zone times 2.1 inches per foot is 14.7 inches of possible storage in that particular orchard. We know that in our management approach, we probably do not want to chance using all of that water to keep, and we wish to keep the crop in a relatively unstressed condition and performing at its best. So I'm going to use this 50% management threshold. Again, that's a judgment call. So at a 50% threshold, we have about 7.4 inches of water holding capacity for this particular situation. So I'm going to take another knowledge check here and ask you to consider this question. Second orchard, A2, almond orchard, is an arbuckle gravelly loam with available water storage of 1.6 inches per foot. Our best estimate is the effective root zone is 4 feet. What is the plant available water given that set of conditions? So we're a little under 2/3 think 3.2 inches is the right answer, and 1/3 6.4 inches. Okay, and I'll show you on the next slide. Just remember this 50% management threshold was a condition that I had set. Again, a judgment call. Let's see here. So here's the math for the question. 4-foot root zone, 1.6 inch per foot, so 6.4 inches of total plant available water. making the provision for a 50% management threshold. That works out to be 3.2 inches of water in storage that we have to manage and work with in terms of water holding capacity. So the 61% were correct in this situation. So this raises the question, so that after we get an idea of how to assess our total plant available water and the water holding capacity of the soil, this raises the question of will the orchard be refilled at the start of each season? And I think we, at least in the Sacramento Valley, you can see this is most of our valley floor, the lighter green. That you can see a lot of our area averages 15 to 20 inches of rainfall. So in the Sacramento Valley, that's indicating a pretty good chance that most years, for most of these soils, we are going to have enough winter rainfall to have that kind of storage that we've been talking about in these examples. I know some of the audience is from further south, and so as you move into the San Joaquin Valley, that starts to diminish 5 and 10 inches. In the Sacramento Valley, I would say 1 or 2 out of 10 years, we get a strong enough of a drought that it challenges us to refill. That's why sometimes you will hear or you'll read myself and my colleague Luke Milliron, whom is also on this call, and I just realized I forgot to introduce earlier, farm advisor from Butte County. We will write sometimes about considering irrigating in the winter to do the work that the rainfall is not doing during a drought time. So we can weigh in the probabilities where we live and how much average rainfall we get and the probabilities of receiving it, but it ultimately boils down to going out and looking if you don't use soil moisture sensors, okay? I put this slide in just to remind all of us that there's at least one very good online source, free. If you Google USDA estimating soil moisture, there's a nice colored publication that will walk you through how to auger and handle soils and evaluate the available water content so you can kind of judge how well those soils are refilling. So one of the key points of this presentation is to make the connection between our ET reports and with the soil water availability and the soil perspective. So now I'd like to take you through an example, a hypothetical example of how to use these reports. I guess I shouldn't say too hypothetical. This is real soils and real ET data from the Sacramento Valley. So I selected almonds for the just last week, the April 10th to April 16th report. And I am using the Arbuckle soil series that we just worked through, that 3.2 inches of available water at 50% management depletion. And so the thought process is something like this. The orchard's located in Tehama County. The soil from our assessment has 3.2 inches of available water at 50% management threshold. Through April 16th, our ET estimates accumulated to 3.9 inches. Our weather records recorded since the almond leaf out date of 3/1 is 2.66 inches. If we do the math, I'm going to back up here for a minute, 2.66 inches. And then I adjusted only accounting for 50% effectiveness, or 1.33 inches. This adjustment I'm making based on my experiences over the years. When I credit the full rainfall, I typically find that the water budget falls behind and that the soils are actually drier than I expect them to be based on the water budget. So I use a 50% adjustment factor. There are various variables that might cause the rainfall to not be effectively stored and available to the trees to meet the ET demand. So the math is like this: 3.2 inches available water, minus 3.9 inches of ET, so the 3.2 from the soil storage, 3.9 from the ET, 1.33 from the rain. This points out that we are about 0.6 of an inch away from reaching that 50% depletion, that management depletion. And it raises the question, might we wait another week or begin irrigating? And if not, how much water might I apply? So we're really close to here, as I pointed out, to that 50% depletion. Points back to next week's estimate of ET in our report is 1 inch. It would suggest if we waited another week that we would go past that management depletion goal. So we might want to irrigate sooner than waiting, but if we did choose to wait, it would not be an overreach by too much. So again, this is the thought process. It's trying, the whole point of this is not to be perfectly exact, but to keep you thinking about where do I think I am in the irrigation process. So we're definitely close to the need for irrigation. So this is knowledge check number 3. We're closing in towards the end here. The question is, in your estimation, if Orchard A1 was located in Colusa County, Williams, instead of Tehama County, Gerber, would it be time to begin irrigation?
Alan, is it possible for you to go back one slide to show the Williams numbers?
I'm sorry, I'm sorry, Kat, I'm having troubles hearing.
To show, is it possible to go back one slide to show the numbers for Williams from the report?
Yeah. There you go. So Colusa County, the far right. Okay, so this was admittedly a tougher question, okay? I will walk you through it. We're approximately evenly split between yes and irrigation is overdue, no, continue to wait, it's not yet time to irrigate, yes, irrigating now is perfect timing. I'll close this and we'll walk through and maybe talk about it for a second. Okay, so here's the thought process. You have 3.2 inches of at 50% management threshold to work with. Remove this bar. Now the cumulative ET is higher at Colusa County than in Gerber, and the rainfall is substantially lower. So 4.35 versus only about a 1/4 inch of effective rainfall. We do the math, 3.2 stored in the soil, 4.35 as ET, 2.26 put back as rain. What this calculation suggests is that we are almost an inch past the 50% depletion. So based on this calculation, you would probably answer that yes, it's time to irrigate. And if you're firm on the 50% depletion, you would say we are overdue. Okay. If you were of the mindset that you were comfortable with delaying longer, you might answer it's perfect timing. Okay. When I created the question for discussion purposes, I mostly wanted to show that how our ET reports pick up on the differences in climate between the two weather stations. And in this case, it looked as though you might be irrigating earlier further south than to the north this particular season. Okay, so kind of moving along, somehow I stretched things out talking too much here. I want to move on to the next question of pairing a water budget with soil moisture monitoring. Just going to give you a couple little examples. So this is a second leaf orchard. The picture on the left was taken in May of 19, last season, September of last season. This is a graphic if you were to set up a little Excel spreadsheet and keep a weekly record of your ET reports, except it's adjusted for partial canopy, which will be a discussion of a later tutorial in the coming weeks. The cumulative ET from April to October is about estimated to be about 26 inches, while the applied water was over 20 inches, around 21, suggesting about a 4-inch difference between ET and that applied. And for this particular orchard, probably within reason that soil storage could cover the difference comfortably. This graphic to the right is using watermark soil moisture sensors. I'm sorry, not using watermark soil moisture sensors. This was actually using a neutron volumetric soil moisture device, measuring the water content in 1 foot increments down to 8 feet, and on approximately a weekly basis. And the point of this graphic is these are your shallower soil depths down here. The surface foot, 2nd and 3rd foot. Up here, the blue is your 4th foot, and then these are your 5th, 6th, 7th, 8th foot. The main point of this graphic is, as the water budget suggests, we closely matched ET with applied water, and our soil water content measurements are pretty steady. We got one little blip here that I cannot explain. I tend to think it was an issue with our operation of our monitoring device that day. But the point is, there's pretty good agreement between the water budget and the soil moisture sensors. This is a second orchard, 1 year older, so 3rd leaf. And in May, in September, similar data, okay? Here you see the cumulative ET topping out at about 35 inches. Here you see the applied water and substantially less, on the order of about 12 inches less than the cumulative ET. This is the same weekly soil moisture graphics. This is your surface soil. This is your 2nd foot, your 3rd foot. Your light blue line is the 4th foot, and then the other lines are the deeper. Unlike the previous graphic, all of these different zones are losing moisture from spring to fall, on the order of about 1 inch or 2 per zone. And it starts to match up, and good agreement with the difference, or the within the water budget, okay? So again, this is a case here that maybe both the water budget and the soil moisture sensors are suggesting that possibly more irrigation might have been appropriate, but at least they were in agreement. So this is our final polling question. The question is, why might an irrigation manager pair ET water budget information with actual soil moisture monitoring to help guide irrigation So there's the final results. So the large majority picked the third answer, that both answers A and B are good reasons for pairing them together. That is to take advantage of the strengths of both and recognize that each has limitations. Okay, I did want to back up for 1 second. There was a thought that escaped me. This is a soil moisture graphic in this third leaf that points out that we see evidence here of the soil profile and root activity drying at least into the 5th, 6th foot by seeing these gradual trending dry downs from spring to fall. Sometimes that surprises folks. Okay, last topic, how to adjust for different irrigation wetting patterns. So the common question that I'll get is, since I don't irrigate the entire orchard floor, do I need to apply more water to compensate? So here is solid set sprinklers, commonly used in walnut, the Nelson 2000 series. Here you can see different situations in almonds with the micro sprinkler with the cap, micro sprinkler with a partial wetting pattern here. To answer this question, I referred back to a illustration that I used in the first tutorial. We can't see a crop evapotranspiration, but if we could, it would look something like this, with the sun beating down on the crop, providing the energy to, and the wind providing the energy to the gradient for transpiration to occur, and it is then leaves the canopy as kind of across an entire surface. Usually this transpiring surface is much larger area than the partial wetting patterns that you see with the irrigation systems. And so if anything, when we use an irrigation method that reduces the wetted area, we will reduce the rate of ET by reducing the soil evaporation, having more dry soil that doesn't have water to evaporate away. And this will reduce the amount of water, the applied water needed. My thought on this question of that you do not need to apply more water to compensate, but it is necessary to irrigate differently. Smaller wetted areas translate to lower water application rates. This translates to more hours of irrigation to apply equal amounts of water and match the same weekly ET. Consequently, it may be necessary to irrigate more often each week. Soil intake rates will control. Typically, we can't irrigate soils much longer than 18 to 24 hours. They become saturated at the surface, and that generates runoff. It's possible that you get such a vertical movement of the water and it doesn't move sideways, that you may actually have percolation deeper than where most of your roots are. And there's also the issue of trying to operate your system within the rate structures of our utility companies. So I'm going to use our calculators real quickly just to make a final point. With the Nelson sprinklers, in this case, this particular system, each sprinkler delivers 1.45 gallon per minute. The number of sprinklers per acre are 45 per acre. It's every other tree, every other row. When we do the applied water application rate, inches per hour, that works out to be 0.14 inches per hour put down with that Nelson 2000 series sprinkler. In contrast, if we were to use a micro sprinkler in the same walnut orchard, it had 18 gallon per hour micro sprinklers, 1 sprinkler per tree. That'd be 90 sprinklers per acre. that works out to 0.06 inches per hour water application rate. So when we do the math with the solid set sprinkler, if we had a week in the summer, 2 inches of ET at 1,400 inch an hour, that's little over 14 hours of irrigation needed at 100% efficiency. This is easily accomplished with 1 irrigation per week, barring the soils don't have a serious intake problem. With micro sprinklers, with the lower water application rate, it would be over 33 hours to apply that same amount of water. So in this instance, you are applying the same amount of water, but you're irrigating differently. You may need to split into 2 irrigations per week to manage the infiltration and the time of use rates of your utility company. And so that kind of works us through the tutorial on relating our crop ET reports to soils. It's time to wrap up. Would like to thank you. We're planning to do a third tutorial in about 12 days, Friday, May 1st, from 3 to 4 p.m. In that instance, we'll talk and think about using the crop ET reports from the perspective of tree water status, measuring the tree stress. So with that, I'd like to say thank you.